In this section, we're going to be finding roots of complex numbers. Roots of them, like the cube root of, 3 plus square root 3i. Things like that, okay? Roots of complex numbers. Or maybe the sixth root, or the square root, things like that, okay? So, to begin with, the fundamental theorem of algebra states a polynomial of degree n has n solutions in the complex number system. So this equation has 6 solutions in the complex number system. We know what 2 of them are. X equals 1 and x equals -1 will satisfy that equation, right? But there are 4 more. 4 more solutions in the complex number system. I know there are because that is the fundamental theorem of algebra. Okay? So, definition of the nth root of a complex number. Because we're going to need to use the trig form of numbers in order to find all of their roots. Okay, the complex number a plus bi is an nth root of a complex number z when if you raise a plus bi to the n power you get u to the n. You get this to the n. Okay? Writing a complex number in trig form helps us to find all of the n roots of a complex number. Let's consider this complex number, -16 plus 0i, which is the same thing as, we shouldn't need to go and do any work to get that. -16 is just over here. That is where theta is pi, r is 16. So hopefully when you see this, you do not need to do a lick of work to write that in complex form. Okay, let's list all 4 of the 4th roots of this complex number. Okay? The principal 4th root can be written as this, which would be 16 to the 1/4. 16 to the 1/4 is 2, and then multiplying the power to the argument, cis of pi over 4. That would be 2 times cosine of pi over 4 plus sine of pi over 4 I, or square root of 2 plus square root of 2 I. Let's graph that solution on the complex plane. So I'm going to go to the right, square root 2 over 2, and I'm going to go up square root 2 over 2. And that would be that solution. Okay, the other 3 roots, this is key, the other 3 roots are distributed evenly about the plane. So if this is a root, and I need to place 3 other points on here, distributed evenly around the plane, where must they be? Well, they must be here, here, and here. It's the only way that they would be distributed evenly about the plane. So this is negative square root of 2, and this is negative square root of 2i. So the points must be negative square root of 2 plus square root of 2i, negative square root of 2 minus square root of 2i, and positive square root of 2 minus square root of 2i, along with this one. Okay? We're going to be seeing patterns in what we're doing, but this is key, that these are all distributed evenly. Notice we have n roots, we have n points. Those are all 4 of the solutions. Okay, in this case it was very obvious where the points would be, but sometimes it is not so obvious. So we need a more generalized way to write these other answers. Okay, we're always going to get that first answer, and that is key. So I'm going to write the first answer as 2 cis pi over 4. Okay? And I'm not adding anything to that. However, I'm going to leave this, I'm not going to put this bracket on quite yet. To get to the next point, to get to that point, that next angle, do you agree, is going to be 3 pi over 4. I'm going to take my original pi over 4, and I'm going to add to that 2 pi divided by the number of roots that I'm finding. 2 pi over, in this case, 4, because I had 4 roots. N was 4, okay? And I want to do that, okay? My next one, I need to add another pi over 4, true? I need to add another pi over 4. So I'm going to have my initial pi over 4, and I'm going to add another one, okay? I said pi over 4. I'm adding pi over 2 each time, which is 2 pi over 4. So here I needed one of them. Here I didn't need any of them. And then for my last one, I need to add another pi over 2. So my initial pi over 4, and then another pi over 2, which is 2 pi over 4. This will always get me all of my roots, okay? 2 pi, because that's how far we go to get around the whole thing. That's 2 pi. That's this one. And then you always divide by your number of roots that you're finding, okay? Start out with 0 because you want that first one to be untouched. And then go up to 3. In this case, it's always going to be n minus 1 that you stop at. Okay? So that is the formula for finding the nth roots of a complex number. Okay? That's it in formula form. Okay. All right, let's determine the square roots of this complex number. So I have 36 cis pi over 3, and I think of that as I want the square roots, so that's a power of 1/2. So the first thing I do is I take the square root of 36, which is 6, and then I start my cis's. Okay, the first argument will be 1/2 times pi over 3. 1/2 times pi over 3 is pi over 6. And to that, I don't add anything, but I'm going to write that as plus 0 times 2 pi divided by n. N was 2 because we wanted the square roots. For square roots, n is 2, and we will have 2 answers. And then I have one more answer. I keep my pi over 6, and I add one more of this 2 pi over 2. This is going to give me 6 cis of just pi over 6. This will give me 6 cis of pi over 6 plus 2 pi over 2. Well, common denominator, I'm going to do this in my head. Common denominator is 6, so this also must be a 6. And 6 pi plus 1 pi is 7 pi over 6. That is 6 times cosine of pi over 6 plus sine of pi over 6i, and cosine of 7 pi over 6 is negative square root 3 over 2. Sine of 7 pi over 6 is minus 1/2 I. So this will be 3 square root 3 plus 3i, and this one will be negative 3 square root 3 minus 3i. Think about where those are located on the graph. The angle is pi over 6 and 7 pi over 6. Pi over 6 and 7 pi over 6. Yeah? So those would be your two evenly distributed roots. Okay? So the square roots of 36 cis pi over 3 are 3 square root of 3 plus 3i and negative 3 square root of 3 minus 3i. Those are the square roots of that complex number. Okay, so when you are finding all of the nth roots, number one, write the complex number in trig form. Write it in trig form. Find the nth root of your real number, and then write the cis expression for the n roots. So this will be the nth root of r, and this will be cis theta divided by n plus 0 times 2 pi over n. And then you keep on going with this same argument, part of the argument, and then multiply by 1, and then multiply by 2, and then multiply by 3, oops, then multiply by 3, and you keep on going until you get, to theta over n plus whatever n minus 1 is times 2 pi over n. Keep on going till the number before your n. And then you'll put the nth root of r out in front. Should have had that in front of all of these. Okay, and these will be the n roots of your complex numbers. All right. A few more little examples. Okay. Let's determine the fourth roots. So n equals 4, and we will have 4 answers. 4 roots. Okay. Of this complex number. We're going to write our answers in reduced trig form. So we're going to leave it in cis form. Okay? All right. So in my mind, I start off thinking of, I have 81 cis 3 pi over 5, and it's the fourth roots, so 1/4. The fourth root of 81 is 3. And then I multiply this 1/4 to my argument, and I get cis of 3 pi over 20. That will be my first root, my first answer. But I'm going to go ahead and start my pattern. Plus 0 times 2 pi over n is 4. My next one will be 3 cis 3 pi over 20 plus 1 times 2 pi over 4. My next will be 3 cis 3 pi over 20 plus 2 times 2 pi over 4. You can tell I've done too many videos today. My handwriting is getting very sloppy. 3 cis 3 pi over 20 plus 3 times 2 pi over 4. If we go one more, we'll be back to that one because we'll have gone around the block. Okay? So stop there. Those are your 4 answers. Okay, so this will be 3 cis 3 pi over 20. Okay, this will be 3 cis. Okay, common denominator is 20, right? So I'm going to have a 20. Common denominator is 20. I need to multiply the 4 times 5, so I'm multiplying 2 times 5 and getting 10. Add that 10 pi to this 3 pi, and that is 13 pi. Next one. Common denominator is going to be 20. Okay. Okay. 2 times 2 pi is 4 pi. But then I need to multiply that by 5 to get the 20, right? So 4 pi times 5 is 20 pi, plus 3 pi is 23 pi. Finding common denominators and just adding. 3 cis. Common denominator is 20. 3 times 2 is 6. Multiply by 5 to get our common denominator. So 6 times 5 is 30, plus 3 is 33. That's our answer. Those are our answers. Those are the fourth roots of 81 cis 3 pi over 5. Notice something about these, you guys. What do we do to that to get to that? We add 10 pi over 20. And then we add 10 pi over 20 again. And then we add 10 pi over 20 again. If we added another 10 pi over 20, we would be back to that one. Those are evenly distributed about the grid, the plane. Number 3. Let's determine the sixth roots of -7. The sixth roots. The sixth roots. N is 6. So we're going to have 6 answers. Okay. First thing I want to do is write this in trig form. Well, I know what -7 is. -7 is just a real number. It's out here on the -7 on the real axis. That is when theta is pi and r is 7. So it's very easy to write that in cis form. We should not have to do any work to get there. Just visualize where it's at and what your angle is. So this is 7 cis of pi. Okay? And I want to find the sixth roots of it. Okay? So I first have the sixth root of 7, which is just the sixth root of 7. And then it's cis. Pi times 1/6 is pi over 6. Plus 0 times 2 pi over n is 6. Right? That's going to give us the first answer. And now we do the second one. Cis pi over 6 plus 1 times 2 pi over 6. 7th root of 7 cis pi over 6 plus 2 times 2 pi over 6. 6th root of 7 cis pi over 6 plus 3 times 2 pi over 6. 2 more. Last one. I stop when I get to 5 because if I go one more, I'll be back to this one. Okay, let's clean up. This sixth root of 7, cis pi over 6. The sixth root of 7, cis. 1 times 2 is 2, plus pi, plus that 1 pi is going to be 3 pi over 6, which is pi over 2. 6th root of 7, cis. Okay, 2 times 2 pi is 4 pi, plus 1 pi is 5 pi over 6. 3 times 2 pi is 6 pi, plus 1 pi is 7 pi over 6. 4 times 2 is 8 pi, plus 1 pi is 9 pi over 6, that is 3 pi over 2. Square root of 7 cis, Okay, 10 pi plus 1 pi is 11 pi over 6. All right, that is the 6th root of 7. Cosine of pi over 6 is square root 3 over 2. I'm going to write that as square root 3 over 2. I'm going to save myself a line. I'm going to go ahead and distribute. I'm distributing that 6th root of 7 into the two terms that I get. Plus square root of 7, I'm sorry, not square root of 7, 6th root of 7 times sine of pi over 6 is 1/2 I. Okay? Here we're going to have the 6th root of 7 times cosine of pi over 2 is 0. I'm not going to write times 0. It's just 0. And then I go to the next part. Sine of pi over 2 is 1. And then I have the I. Okay? Let me, for the sake of your notes, write that as 0 plus 1I. That's just going to be the 6th root of 7I. Okay? Here we're going to have the 6th root of 7 times cosine of 5 pi over 6 is going to be a negative, so negative 6th root of 7 times square root of 3 over 2 plus sine of 5 pi over 6 is 1/2 times the 6th root of 7. That's going to be the 6th root of 7 over 2I. All right. For this one, cosine of 7 pi over 6 is a negative, square root 3 over 2. Sine of 7 pi over 6 is also a negative, 1/2. Put your eye on. 3 pi over 2. Cosine of any pi over 2 is 0. Cosine of any pi over 2 is 0. So that's going to be a 0. Plus, sine of 3 pi over 2 is negative 1. So this is going to give us a negative 6th root of 7I. Cosine of 11 pi over 6 is positive. So we'll have a positive 6th root of 7 times square root of 3 over 2 minus, because sine of 11 pi over 6 is a negative, 1/2, so square root of 7, 6th root of 7 over 2I. All right, these are the reduced standard form 6th roots of negative 7. I want to, before we leave this, think about where are these located? Where are these guys located? Well, we have pi over 6, all the moduluses are the same, the R values are the same. So pi over 6, and then we have 7 pi over 6. Pi over 2, and 3 pi over 2, right? 5 pi over 6, and 11 pi over 6. Do you see how those are evenly distributed around the grid, okay, around the plane? Alrighty. One last example. Let's determine the cube roots of this complex number. First thing we're going to do is write it in trig form. So I need to think about where that's located. Where is that located? Positive 4, negative 4 square root of 3I. So it's in quadrant 4. So I need to put my theta in quadrant 4. Right? So R is going to be the square root of the square of 4 is 16 plus the square of 4 square root of 3. That is 16 times 3, or 48. That's going to be the square root of 64. Oh, that turned out nice. We get a nice even 8. All right. For theta, tangent of theta is b over a, negative 4 square root of 3 over 4. So tangent of theta is negative square root of 3. We're in quadrant 4, so theta is the pi over 3 in quadrant 4, 5 pi over 3. So I have 8 cis 5 pi over 3, and I want the cube roots. N is 3, and I'm going to have 3 answers. Of that complex number. Reduced trig form this time. Reduced trig form. So we're just going to leave it in trig form. We're not going to find the standard form for it. Okay, so my first one will be the cube root of 8. The cube root of 8 is 2. Cis, multiply 1/3 by your argument, and we get 5 pi over 9. Now I know why they said to leave it in trig form, because we don't know, without doing some work, we don't know what cosine and sine of 5 pi over 9 is. Plus 0 times 2 pi divided by n. N is 3. That'll be one of our answers. My next one will be 1 times 2 pi over 3 in that spot. And my last one will be 2 times 2 pi over 3 in that spot. This first one will be 2 cis just 5 pi over 9. My next one will be 2 cis. Okay, common denominator is 9, right? I need to multiply that by a 3, so I multiply that by a 3. 6 pi plus 5 pi is 11 pi. Next one, common denominator is 9. I need to multiply 3 times 3 to get 9, so I multiply on the top by a 3, and then I also will multiply the top by that 2. So I have 4 times 3, that's 12. 12 pi plus 7 pi is 17 pi. We should always be adding the same thing to get to this one, to get to each one. So it's 5 pi over 9 plus 6 pi over 9 gives me that, and 5 pi over 9 added to the, 6 pi over 9 added again will be 17 pi over 9. So I know I'm correct. I know that these are evenly distributed. If we added another 6 pi over 9, I would be back to the 5 pi over 9. Okay, that's it for finding roots of complex numbers.